So when we left off last time, we were talking about the 5 ways to evaluate limits by hand. We talked about the first 4 methods: direct substitution, factor and cancel, rationalize and cancel, and the trig limits. And now we're going to talk about the 5th way to evaluate limits, and that is our last resort option. You tried methods 1 through 4, nothing worked. This is the only time you would use this case, and that is we have to make a table. We have to make a table of values with values close to the value that's not working out, and we pretty much just go from there. So let's just look at an example of this. Let's say I have the limit as x approaches 4 of x over x minus 4. Okay? Here we use direct substitution. We're getting 4 minus 4 in the denominator. We get 0. That's not going to work out. Then we think about factoring and canceling. However, we really can't factor or cancel anything here. It's already in its most simplified form, and you cannot cancel out the x's here. You cannot do that. That is a very wrong thing to do in math, so don't do that. We're not going to rationalize and cancel, because the whole reason we do rationalize and cancel in the first place is because we have a square root symbol. And since I don't see any trig, no sine, no cosine, it would be impossible to use the trig limits. So now we're kind of left at a crossroads of how we're going to solve it. And the answer is make a table. And specifically, we're going to make a table with values close to 4. So here's what I would recommend you do. I would say you have x, and then you have f of x, the y values. And I would choose numbers close to 4. So let's choose 2, 3, 4, 5, 6, and let's see what happens in each of those cases. So, first of all, with 2, if we plug in 2, we get 2 over 2 minus 4. It's going to be 2 over negative 2, which is just negative 1, so we get negative 1 for 2. Now let's do 3. 3 over 3 minus 4 would give us 3 over negative 1. That's negative 3, so negative 3 there. Negative 4, I'm just putting a question mark because, again, we're getting 0 in the denominator. We can't have that. I'll just put a question mark there, it doesn't matter. 5 is going to be 5 over 5 minus 4, which is just 5 over 1. So we're getting 5 for that. And then 6 is going to be 6 over 6 minus 4. That's going to be 6 over 2, which is just 3. So we have some values. We have our table here. And now let's go ahead and draw a graph and actually plot those points on that graph and see what's going on here. So we have x and we have f of x. And so for the x values at 2, I should have done that better. So we have our x and y axes like this, x, f of x. We're going to be plotting on 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And then we have the y values, 2, negative 1, that's that point right there. 3, negative 3, so negative 1, negative 2, negative 3. We get 3, negative 3, like this. 4, we don't know what's going on yet. 5 has the point 5, so 1, 2, 3, 4, 5. 5 comma 5 is right about there. And then we get 6 comma 3, which is right about there. So there are our 4 points, and if we think about what's going on for this graph, even if you have no idea what the shape is, I will tell you this. Do you remember what a vertical asymptote is? You know it's the dashed line that goes vertically, but how do we know there's a vertical asymptote? Just by looking at the function. If you remember, vertical asymptotes come from wherever the denominator is equal to 0. And so for that reason, we know what's going on at x equals 4. X equals 4 is a vertical asymptote. I'm going to write VA for vertical asymptote. And if we have a vertical asymptote, how do we represent that on the graph? We remember it's that dashed line going up like this. And once we see that dashed line, we can kind of think about how we would connect these dots here, because we know as it's heading towards 4, it's either going to head towards positive or negative infinity. And once we have these dots here, we can kind of see the trend that's going to go something like this. It's going to head towards infinity from the right and negative infinity from the left. And once we have the graph, this comes back to computing limits by looking at graphs, and we already know, first of all, hands down, if it's heading towards infinity on either side, the first thing we would write is does not exist. It does not exist. It doesn't matter if they match with positive or negative infinity. In this case, this side's heading towards negative infinity. this side's heading towards positive infinity, that's the other reason why we know the limit does not exist, because it's not approaching the same value. But what I'm trying to tell you, and it's super important that you recognize this, that even if we did have another side heading towards negative infinity or positive infinity, even though both values are negative infinity, we're still going to say the limit does not exist. The limit cannot exist when x is approaching positive or negative infinity. That is just the rules of limits. And so that was a good example problem. And now let's just talk about, how would you use these methods in terms of solving limits for any limit you see. So again, the 5 ways to evaluate limits. The first way you should try, hands down, at least think about it in the back of your mind, is direct substitution. You should try that first. 99% of the time, there will be an error. There will be a 0 in the denominator or something will go wrong. And we need to recognize that though, that direct substitution is the first way we should try. And steps, 2 through 4 really depend on what you have available to you. Like for instance, if you have a square root, you're probably going to use rationalize and cancel. If you see sine or cosine, you know you're going to use a trig limit. And then as a last resort, only as a last resort, you would make a table. And that is the strategy for solving limits by hand using the 5 strategies of solving limits. My name is Dan the Tutor. Thank you for watching, and we'll see you next time.